those things. I have some pain. I have to take an injection of, it's called thymus something, and BP 157, and it's PPS it is pentose polysulfate, and they all help, but it's a pain doing it. It took a long time. Anyway, so first, any questions about anything? Well, the last section we covered was section 3-2.2, and I think, I straighten you out with that thing I sent you?
You did, yeah,
Okay.
I worked through it again.
Most of the time when you're dealing with these problems, this is my suggestion, at first it may seem completely baffling. That's the way it is with a lot of stuff. And it gets more and more abstract and complicated the further we go. In chapter 5, you're going to see some of these things you're looking at, you don't know where to begin unless you have done all the previous work, because it really is something that is confusing. But if you keep up with it, the next logical step is the next actual thing that you see. Yeah.
So for the midterm, are we going to be able to have a formula sheet?
No, never. You get, it's absolutely closed book, closed notes. Closed book, closed notes. If anything you need, and some of the, like, if you want tables, I'll give you tables, but I think everybody has calculators right now for Gaussian stuff. You know, the Gaussian stuff is very important, but for the Rayleigh, you don't really need tables, because the Rayleigh, the cumulative distribution function is just 1 minus that e to the minus r squared over 2 sigma squared, and that sigma, of course, is the Gaussian sigma, and that's important to recall. But for the Gaussian stuff, you have to either have tables or you have to have a calculator and know how to use it. There's no way that you can do that close form. I mean, with anything where you can get a close approximation. Now, you did all the problems. Section 3.2 had problems in it. I'm going to just, unless somebody has another question. In problems in section 3.2, like 3-2.1, did you all try this stuff? All right. These are conditional probability problems, but there's one particular thing that's important. There's always noise, and noise will have a distribution. In fact, in the real world, I'm going to say this. You've heard of white noise and stuff? That's a noise spectrum that's known. And by the way, these things are based on statistical science. It's amazing how accurate this stuff is. Once you know something about the noise, you can do a whole lot to infer, if you measure something that would be like a y, what in fact x was that was sent. This is really important, the most likely value stuff. So for this one, if you don't mind, we'll start with 3-2.1. Do you have that?
Yeah. A signal x has a Rayleigh density function and a mean value of 10, and is added to noise 10. That is uniformly distributed with a mean value of 0 and a variance of 12.
Wait. Stop here. We got Rayleigh, right? For a voltage or something?
A Rayleigh density.
All right, we'll call it
Signal
x. Mean value of x. Stop for 1 second. So that's square root of pi over 2 sigma. And I'll just put sigma of x. You know it's the Gaussian sigma. You all know these are things you should know how to do quickly. And then you said we got noise, right?
Yes.
And it's uniformly distributed?
Yes.
All right, slow down for 1 second. So I'm going to say noise is uniformly distributed, and from where to where?
Mean value of 0 and variance of 12.
All right. Now, the minute they give you the variance of noise with a constant value, this would be the constant value here. We need the spread, and we know it has a mean value of 0. So that means it's going to be centered about the origin of this, whatever the horizontal variations. Do you follow me, class? Now, if you have that, we need this. If you think back 2 lectures, I gave you something that if you had, I'll put this over here to jog your memory if you don't recall. If you had something and this is A, this is B, the height here would be 1 over A minus B, and I'll call that C. And if you remember the average value of this function, I'll just call it f of x, make this x here. The average value of this is simply A plus B over 2. Do y'all remember that? Be doing this for a constant value? And then, remember that the standard deviation, or variance, I should say, variance, not standard deviation, was equal to the change, or it's equal to b minus a squared over 12. Do you remember me doing this, class? How many do? All right, these are things you need to know, okay? I'm telling you this. But the way to think about this right here, anytime it's a constant density function, the variance is just delta, or the difference, if you have a constant density, it's the spread, the delta difference between the upper and lower bounds, squared divided by 12. You can prove that. It's not hard, but those are the two things, this and this, the mean and that. Now this is for noise, right? And what else did they give you?
X and N are statistically independent and can be observed.
Okay. All right, so noise is statistically independent of the
signal.
the signal itself, X, and then they observe Y equals X plus the noise, isn't that right?
Yeah, that's correct.
This is kind of a classic problem. By the way, noise, in some ways, if you have a very small bandwidth, you'll get a constant value for the density function. All right, it's just, that's the way it is. But if you get wideband, it will be Gaussian almost always. If it's naturally occurring noise, it will be Gaussian. So anyway, and the two forms that you always need to be aware of for noise and be able to do the calculations are Gaussian distributed noise with zero mean. It has to, with maybe an exception of something with a diode, a rectification, it's always going to have zero mean for noise. In space, any kind of radiation, stuff like this, zero mean. But the spread itself is something, I mean, I should say the shape could be Gaussian or could be constant, but it's symmetric, and that's important. Okay, I think. Okay, now the first thing we need to do over here, since this is the density function for the noise, right? This is f of n here, is I need to find what A is. Can y'all follow me, class? If you look over here, that's the key. Because we know the spread is 2A. Did I put that 6 down here? You said something that the noise, standard deviation, or I should say variance was, is it standard deviation or variance?
The variance is 12.
All right, variance is 12. So if you have that, you come over here and I'm going to point to that formula. If you've done this, you know what I'm doing already, but I'm just trying to refresh it. So I'll start with sigma squared is equal to the delta x squared over 12. I know that is 12. And that's equal to delta x. Now, that's the spread. It goes from minus a to a, so it's 2a. Do y'all agree with this? So we've got 2a squared over 12. And that's going to be 12 squared is equal to 2a squared, or 12 is equal to 2a, or a is equal to 6. And I think that's right. I think I posted the solution to this. Y'all follow me on this, class? You guys, are you with me on how this works? You use what you know, constant density, that's the variance, that's the mean value. We're talking about just the noise here. So once you have this, now you have the spread, called spread in the noise, it goes from minus 6 to 6. With me? Now after that, they wanted, what was the next thing?
Find, sketch, and label the conditional probability density function for f of x given y as a function of x for y equals 0, 6, and 12.
All right. Now in there, you remember when we did conditional densities, we used Bayes' theorem? Remember, probability of A given B is times the probability of B is equal to probability of B given A times probability. You don't remember that? You can break it down to the actual density functions. And in that, in the PDF, he does a discussion of this. Did anybody look at that and read it? In the PDF, his discussion of how to develop that? No. Well, it's very straightforward, but he will have, like, if you want f of x given y, that was his take, right? That's what he said. That's what he wants, right?
Mm-hmm.
Well, you know this is gonna be, I'll just tell you what this is gonna actually come from. You're gonna have an f of y here, f of y. And this is gonna be f of y given x times f of x. It's the way it's going to be. I'm going to rearrange that, but that's the starting point. You can play with that and prove it. If you start with the Venn diagrams, you can get down to this in differential form. So that means f of x, whenever you see that slash y, it means y is known. We have an observation. When they say f of x given y, we measured something, we observed something. Now we're trying to actually figure out what was sent with the noise, most likely value. And that's going to be equal to f of y given x. Yeah, f of y given x times f of x over f of y. And I believe this is what he'll have the form of in the book or in the solution I posted. Y'all with me, class? Remember, it comes from this, from here. Okay, once we have that, next step is how do you relate the noise? This density right here, this C right here, is going to be equal to 1/12. That's going to be the height of that density for the noise. I'm going to stop for a second, make sure everybody follows me. We need to figure out what density function the noise is to go ahead and go further down the line with this problem. But once we have that, then we can say, using this formula, since I have f of n of the noise is equal to 1/12, and this is from -6 greater to the noise less than 6. Now, and then 0 else. Now I can say that since noise here is just equal to y minus x, now I stick that in there for this. Now I say that f of n of y minus x is equal to 1/12. And let me do one thing. Let me get rid of this. Is equal to 1/12. And that would be for -6 greater than y, minus x less than 6, and 0 else. Now what that really is, and this is where I'm going to stop and make a point. This is y, or this is f of y given x. So we want the density function right here for y given x, and that is this now. It was f of n, but now think about this. We observe y, follow me? And then x can be stated. For whatever x is, we have this density function. Follow me, class? Because it's really just a skewed noise distribution. Can you follow me? It is a little confusing, but, and I think that's the way it's shown in the solutions. You're going to have to confirm that. I don't remember if he did it quite this way or if he used the capital F, the cumulative distribution. You said?
It gives the f of x given y is equal to, and then x e to the negative x squared over 2 sigma a divided by the integral.
Wait. I haven't done the integration yet. This is just for the f of, should be for f of y given x. There should be an f of n of y minus x right there. I'm pretty sure. I'm almost guaranteeing you that's it.
F of x given y is equal to f of x given x times f of n y minus x over f of y given y, or f of y, y.
E. Where are you looking at this?
Down underneath it, in the OneNote, it's got problem 3-2.1 signal and uniform noise. It's just before conditional PDF f of x given y.
Whoa, 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 whoa. Yeah, this is the density function for x is the Rayleigh. F of n is the constant, right?
Mm-hmm.
No, look on here. Let me show you.
Yeah.
It's from minus, see, it's just
Mhm.
1/12.
Yeah.
Oh, okay.
Yeah.
Anyway, back to this thing. I didn't put up the Rayleigh distribution, but I should have. For the actual, did you have a question?
No, my PDF crashed.
No. Mine does that all the time. But over here, so for it says the Rayleigh distribution is for x, right?
Mm-hmm.
All right, so that means f of x here, call it f Rayleigh of x, would be equal to, and it's always the variable, so I'll put x over sigma squared, exp to the minus x squared over 2 sigma squared. What was the variance for the Rayleigh distribution?
Variance was 12.
No, that was for the noise, wasn't it?
Oh, yeah, that was for yours.
Does he give you the variance?
No,
It just says the mean value is 10.
Yeah, he doesn't give a variance.
For the Rayleigh?
Mm-hmm.
Well, if it's 10, we got it, right? I want to make that point too. If he says the mean value for the Rayleigh distribution is 10, the mean value is defined as square root of pi over 2 times sigma x. Follow me? So we have sigma x. So sigma x would be equal to 10 times square root of 2 over pi, and that means sigma x squared would be equal to, it's going to be 200 over pi. Now we've got all the things. There's one trick here though. So for this, since I want that density function, now I have to come over here and I've got to expand it a little. So my f of y of x is right here. And I'm going to have to be careful the way I do this. So it's going to be equal to 1/12, and that is for minus 6 greater than y minus x less than 6, and it's 0 else. And then it's, maybe I should do it this way. It's 0 else. There's no neat way of making that function. That's this one. Now my f of x is right there. So that's equal to x over sigma, which is square root of pi over 2. Or I should say, I'm sorry about that. It's equal to 10 times square root of 2 over pi times exp to the minus x squared over 200 over pi. Now, I have to divide this whole thing by f of y. And if you look at this, right here, my f of y can be gotten from that. And I think this is, take a look at this and see if it's enough. If I want f of y, I have to integrate out that joint thing right there. And that would be my integral from, technically, from minus infinity to infinity of f of y given x, really, y minus x in this case. This is f of y given x, and it's going to be that dx. And I'll put that down here, so it's going to be integral and let's see, put that down there that way. Yeah, I'm sorry, this is right under that, it says conditional PDF for f of x given y, and he has that integral. If you look at that, he has the max of either 0 or y minus 6, all the way up to y plus 6, and then he has, wait a second, I think I did that wrong, I'm sorry. You have to integrate this whole top thing, my bad. That's on me. All right. I better say this correctly. You come over here and do one thing. For this one right here, the f of y, what I had down there was incorrect. You actually have to do the integral of this whole top part right here, dx, and I'll explain why in a second. I'm going to do it right here. The whole idea is this. If, and I'm trying to think where he has it in the book, but if you have a joint density function of x comma y, and you integrate it dx from minus infinity to infinity, then you're going to get just fy of y. And I think we're clear on that. With me, class? So when you have, then he goes through and he says, if I have f of y given x, how many people in the book he's going to have? Be careful about this one. Give me 1 second. If you write this down, this is actually formula 3-11, and it's on page 125 in the PDF. And this is really going to be f of x comma y over f of x. And you should see that in the text in there. Let me check that, make sure. Did y'all see this? I did, you guys show it to you. Or no? You see the PDF? what I'm really getting at is this. This right here is equal to this right here. And now I'm going to say it another way. Over here, this is the same thing as f of x comma y. It's really the density function of both variables, whether they are independent or not. That is the density function. Now that density function is this density function here. Are you with me? This is kind of complicated, all right, because I'm trying to write this in a way. It's either 1/12 if these conditions are met, or it's 0. So the real key is, if we want to get f of y, follow me on this, class? If we want to get f of y, we've got to integrate this function over x. Now, the problem with this is, if you look at this, the value of x determines where the lower integration starts and the upper integration stops. Follow me on this? Because if x, say x is going to be equal to 4, then you would have to say minus 6 would be equal to y minus 4, or you would start at y, you're going to start at a value of minus 2. But you're going to have, it's a sliding window there. Can you all follow me? You'd have to integrate that. I'm going to just put it down like this. It's the integral of this whole mess. So it's basically going to be the integral. It's really that integral. So it's going to be x over 10 square root of 2 over pi. You don't even have to evaluate this integration, thank God. Over 200 pi dx. And then it goes, and it basically has to do with the max value of either minus 6 or y minus x. And it's going to go to the upper value, and that value will be 6, I believe, unless I'm wrong about that limit. Let me check that real quick. It's an odd problem because you don't even have to do the integrations. I'm sorry, y plus 6, my bad. The upper limit is going to be 6 plus y. But when you do this, the whole problem is this has to be realized. So anytime you pick a value of x, whatever that value of x, or I should say value of y, and that determines where you start this integration. You can mess around. Basically, if you go ahead and just break out this, where x starts, you'll find out it's dependent on what the value of y is for this integration. But you're going to have to integrate that from the max value of either minus 6 or y minus x to that. This whole thing is it's getting messy, and so a logical thought you probably have is, are we going to expect to evaluate that on a course? No. Here's what you're going to be expected to understand how to do. Now, what is the question they ask? Next one? That is the density function.
The rest of part A is as the function of x for y is 0, 6, and 12.
All right, now you just plug in the values, and then you get, and didn't I put a plot there too at the bottom in there of the, for the 3 values he gives? Or not?
I don't think you did.
No, they did. And yet, I'm certain I did, but whether it shows up or not.
You gave a table.
No, well, it didn't come in. I did do a plot of this. I did it yesterday. It didn't show up for some reason. Let's see if I can actually take a quick look. All right. I did a plot of these 3 things. I'm not going to expect you to do a plot. I want to be clear about that. Because this is a complicated one. But what's the next part of that? This is the part.
If an observation yields a value of y equals 12, what's the best estimate of the true value of x?
All right. Now, here it gets interesting. whenever you take a look at this noise thing right here, this density function literally became it became the conditional function for f of y given x right here. You all follow me on this? So the limits of this are from -6 to 6, right? And if you look there, he says they want the best value for x, saying if y is 12, right? I'm not going to spend a whole lot of time on this. Remember, we replaced this argument n right here with y minus x, right? So think about this. We observe a value of 12. What would the best estimate be of x? It's going to be 12 on this one. And it's really because the density function is flat right here. It will be, and I think he says that, doesn't he? It's going to be 12. What it's going to come down to is, where is that thing? Wait a second. No, wait. I'm looking at the wrong one here. Hold on. No, I'm sorry, that's wrong, what I said. All right, I'm sorry about that. What he's really asking for is the most probable value. Let me explain that. I'm sorry, I said that wrong. I got it too late. Because this is going to get complicated. And I'm not making it that clear. Back with the Rayleigh distribution here, if you had a variable x, and this is a Rayleigh distribution of x, you know it looks like this. The most probable value here was square root of pi over 2 times sigma right there. Oh, I'm sorry. The most probable value is sigma. That's the mean value. My bad. This is sigma, but it's sigma x. I'm sorry. Do you remember that? So the key is, this is going to be the most probable value. But to get that, you need the mean value. So here's what he's really saying. I need the mean value of that, which is the square root of pi over 2 times sigma. And to get the mean value, now that it's skewed, you actually have to evaluate this, but he says when the observed value of y is
Y is 12.
so now you got to go down here, and if y is 12, this upper part of the integral goes to 12 right here, and this bottom part is going to start at 0. Now, I'll tell you right there, that is going to be this is basically a Rayleigh distribution you're doing here. So you're going to evaluate the Rayleigh distribution, then this will become, this whole thing down here becomes,
Yeah, you said y is 12, right?
yeah.
So would it be 6 plus 12?
Sorry. The width on this one, the width on this one is a maximum width of 12. All right, it has to be 12. So if y is 12, this would have to start at 6 then. It would be, this would be 6 to 18. I'm sorry about that. Check that, because I'm doing this stuff. Y is 12.
That's what it says in the notes. It says integrating from, integrating over 6 to 18, so.
That's on this one. Then this limit two, if y is 12, you'd have to flip that over so you minus 18 and to minus 6, and then you flip the sign. So x would be from 6 to 18 on this integrate, or on this value too, for the limits, 6 to 18. I can tell you this is going to get a little messy, but then that's the conditional probability, but then you need the mean value, so you're going to have to integrate that thing times x to get the mean value of that. This problem's getting a little too out of control right now. I think I was looking at 3-2 when I actually thought about this one. But yeah, he does have an x squared integration in there. Do you see that? This is where he gets that 63.66. See, that integration I'm not going to ask you to do, but that's really going to be something, an integration by parts once, and then you're going to get the Rayleigh distribution. That's over the top for anything I'm going to ask you to do at this point at least. The real thing I wanted to bring out is this. When you have a noise distribution, and this is the next problem, when you have a noise distribution, you can get the conditional probability of if y is observed, what you can get f of y given x, because you need to look at this. We want f of x given y. We see y. We want to know what the density, conditional density is for this. But we need f of y given x, and we get that from the noise. That was the point I was trying to get at. I did it in a very sloppy way. I'm sorry, I apologize. I want to do the next problem just briefly on this one. That problem, I don't know why, all this stuff didn't jump off the page, and this thing was. There might be another way to do this, but I know I was messing with this thing. Okay. The next problem I'll tell you what I'll do, because I want to spend some time myself. I'll exempt section 3-2 from the test. All right. That way, we can focus on 3-1 on backward. And the only reason I'm saying this is because if I can't do a good job presenting this stuff in class, I can't hold you responsible for it. I can tell you that the next several parts here, I know that the real key is the noise distribution and all this, and then you have to go over how to find out if x and y are independent or not, and that comes out when you take a look at if you can separate f of x and f of y into separate parts and just multiply them to get f of x, y. But I did want to talk about, first, any questions about anything we've covered up to this point? Let me ask you that. Few things that I think would be most troubling for people, or at least could confuse people. And it is really going to be related to one of the areas I know is going to be if you have a density function. Suppose I have an f of x. It doesn't matter what it is at this point. It can be anything. If you have an f of x, and now I have a function y equals some, I'll call it y equals some g of x. And g of x can be anything. And now, call it this f of x of x. And now you want f of y of y. This was the one that caused people, you either got it or you didn't with this problem. And there are a couple of situations that crop up. Remember classic that y equals x squared. That is the classic, right? And so if we start, if I say it's a density function and I have f of x for this one, we'll do it over here. So we're going to do this problem, y equals x squared, and I'll say f of x of x. The density function for x is simply 1/10 from -5 greater than x less than 5 and 0 else. And I ask you, first thing I'd ask is what is fy of y, which is a legitimate thing. So this is the classic problem where you got one function strictly positive and the other that can be negative and positive. Following the class? So for this one, probably a smart thing to do, if you can do it, is just graph. If I have x here, and this is why the range of x, really where there's a legitimate density, is going to be from or non-zero density, -5 to 5, and it has a value of 1/10. I look at that and I have both positive and negative, I'm sorry, I graphed that thing. Shouldn't have graphed that thing. Should have graphed the actual functional form. The range of x is from -5 to 5. And if you look at that, y squared will look like this. And here, y will have a value of 25. And x will be 25 also at -5 right here. Follow? That's my own point. So when we did this before, we knew that f of y dy is equal to f of x dx, or I can say fy of y is equal to fx of x and divided by dy dx. But there's some caveats to this that we're going to get at. Y'all follow me? You remember doing this, right? Everybody? So for this one, I have my f of x, and it's just 1/10. And that's from -5 greater than x less than 5. And then dy dx here dy dx is going to be equal to 2x, and x is equal to plus or minus the square root of y. So I come down here, dy dx is 2. It's going to be 2 plus or minus the square root of y. And that means it's going to be 1 over 20 square root of y, but because I have two values of x that give one value of y, I have to double that, so it's going to be 10 here. And then the limits for this, now, does everybody know what I'm doing right here, class? Follow? It's doubled because two values of x, the negative and positive, give one value of y. You're going to have to double this to account for that. And there's an absolute value in the book on this. I just doubled it there. And this would be for y equals 0 to 25. And that would be the density function for f of y. I'm going to keep going on this one. It would be 0 else. Do you all agree with this? Now, the next logical part, and here's where you have to be kind of awake and aware. If I asked you for the mean value or expected value of y, how would you get that? There are a couple ways. Well, what could you could, either way, you can do this, you'll get the right answer. Which one way? We could take this, correct? And we could say, we know it's going to be an integral over the range of y would be from 0 to 25 of, first the density function, which is going to be 1 over 10, and it would be y to the 1/2 power times y dy. Do you all agree with that? And that's a doable one. That would be an equal to the integral from 0 to 25 of, take the 10 out in front, and then you're going to have simply y to the 1/2 dy. It's going to be 1 over 10, and then you're going to get 1 over, and this would be 1 plus 1/2 or 3/2. You could make this just 2/3, and then you would have y to the 3/2 evaluated from 0 to 25. And I don't know what that is, but what is that? 2 over 30 times 25 to the 1.5 power. You can tell me in a second if you don't mind. But there's another way to do that. So the expected value of y is really the expected value of x squared, correct? This is the easiest way. Y'all agree with this, class? And if I do that one, what do I get? Well, I get an integral from -5 to 5, 1/10, right? And it would be just of x squared dx. And that's going to be equal to 1 over 10, and it's going to be 1/3 x cubed, evaluated from -5 to 5. And that's going to be 2/3 divided by 10. And then you're going to have 5 cubed. I don't know what that is, but can you give me this one or that one, either one?
The first one's gonna be 25 over 3.
This one?
Yes, sir.
25 over 3?
Yes, sir.
Okay, you want to give me a decimal value for that too? Yeah.
8.33.
What?
8.33.
That's right. What about this one? Hopefully this thing.
Same thing.
Okay, that's one way to do it. Now, next thing is, if I asked you for expected value of y squared, that's the mean squared value, how would you do it? Now that you saw the first part there. Pardon?
The expected value of x over 4.
Yeah, I would do it that way too. I think it would be easier. You can do it. You can take this instead of y, you could put y squared here, right? But I think it would be easier to just take x to the 4th. And if it's x to the 4th, right there. Now, I think your calculators can do these integrals fairly straightforward. But if you're going to use your calculators to do them, then it can be only right or wrong. You need to show some work, at least to get evidence of what you're doing. But if you have that integration, that's going to be x to the 5th, right? Over 5. And that means this is going to be 1 over 50. And it's going to be 5 to the 5th. And that's fairly big. I don't know how big that is, but it's big. Anybody?
125.
Is that 125?
Yes, sir.
And we could do it over here, but I think it's easier to go that route. This is one of the points I had. Then the last thing is, this is 125. And then how do I get the variance for y? Anybody? You can just tell me in words. What is the variance? So it's the mean squared value, right, minus the mean value squared. So this is going to be y squared bar minus y bar squared. And that's 125 minus 25 over 3 squared. Don't know what that is, but is that right? Yeah, I think it is.
Yeah, it's gonna be 55.556.
Agreed? Did you get that? Okay. Finally, I could ask one more thing about this. I chose this distribution simply because it's about as easy, it can't get any easier than that. It's constant, so there's nothing, there's nothing easier to integrate than a constant. But what if you had, what if I asked this, what's the probability of y being greater than 20? You can do it two ways. But for this one, it might be better to stick with the density for y. Just because the integral in x has got 2 parts. They have, if I say for y greater than 20, right? That would be x equal to plus or minus the square root of 20, right? And you would have to, if I want y greater than 20, if you were integrating with y, it would be the density function for y from 20 to 25. Agreed? Now, if you're going to use x, you have to take the square root of 20, and then you would integrate from the lower limit, which is minus 5, to minus the square root of 20. And you would have to add to that the integral from the square root of 20 to 5. But since you can make arguments of symmetry, or you can take 2 times the integral from the square root of 20 to 5 of the density function for x. That would be the easiest in my opinion. So if you do this, let's talk about making sure we all get the right answer on that one. This is the one thing I wanted to bring up today, because I think there were a lot of mistakes made on this particular type of problem. So for this one right here, I can say the probability of y being greater than 20 is the same probability as, or twice the probability, 2 times the probability of x being greater than the square root of 20. And that would be, and the reason there's 2 there is because there's an upper and lower component of this integration. The integral from square root of 20 to 25, I'm sorry, square root of 20 to 5, not bad, of the density function is just 1/10 dx. That's pretty straightforward. That's going to be 2 over 10, and you're going to have 5 minus square root of 20. And can you tell me what that is?
I got 0.1056.
Is that right, guys?
Yeah.
All right, if you do it this way, it would be the integral from 20 to 25 of the density function of y, which is 1 over 10 square root of y dy. And it's really 1 to the minus 1/2, so you're going to do that, you're going to get 2 over 10 as square root of y evaluated from 20 to 25. You tell me what this is. So that's going to be 1/5. And then you're going to have the square root of 25 minus the square root of 20. Hopefully they'll be the same.
Yeah.
0.1056. Okay. So either way, you're gonna get the right. And to be frank about it, I always try to go the easiest route. And for me, it's whenever you have a constant density. That's just me though. You can do it either way. Let me cover that point. Get to a few others. I'm not going to give you a roulette wheel problem. Just forget about it. And for central moments, remember these are the central moments. So it's going to be x minus x bar to the nth power. All the odd central moments are 0. And the even central moments, remember that formula? I'll put it up here again. The even central moments, take a second to really hammer this home. Because it's easy not to be attentive to this kind of detail. These are central moments. So anytime you have the expected value of x minus x bar to the nth power, they're going to be equal to 0 for n odd, and they're going to be equal to 1 times 3 times, and it's really going to be n minus 1, whatever it is, to sigma to the n. And that's the way it's always going to be for these things. Are you with me on this class?
Sorry, could you say it is 1 times what? 1 times
It's
3?
1 times 3 times n minus 1. So if you think about this, this is going to be for n even. If n's 3, right, then it's really going to be this. If you take a look at this, it really just would be 1 times sigma. I said that right. N even. So it can't be 2. I said. If n is 4, it would be 1 times 3 because n minus 1 would be 3. 1 times 3 times sigma to the 4th power. And that would be the central moments for these. Now, this is a property you should know. This is something you should be aware of, especially like for 4th order moments, that type of thing. And you had a problem with it. I give you something on a quiz with that. I know I did. I forgot it was the last quiz or the quiz before. But that's straightforward, I think. Most of you know that.
And that sigma is it's the normal sigma, not like sigma x or something?
Well,
Or does
this
it
is
matter?
not.
This is different? This is
This is just the standard, or the variance, or I should say, the standard deviation for any distribution you're talking about. Has nothing to do with like Rayleigh distributions. That's just generally true. I shouldn't say it has nothing to do.
I was just making sure that it's not like another different,
See,
because there's a
okay.
lot of different sigmas floating around.
Yeah,
Yeah.
yeah. This is really appropriate for all the density functions. We talked about like Gaussian, all these constant density functions that we really discussed. Rayleigh's unique in the fact that for the Rayleigh distribution, the mean value is the square root of pi over 2 times sigma, and that sigma is the sigma of the Gaussian distributions, but the most probable value is sigma of x. And that's kind of an oddity, if you might think of it. For the Rayleigh problems, they'll be in a class primarily with like marbles rolling or target hitting a target with my probabilities of certain things happening. Give me a second here, I want to make sure. All right, the Gaussian, you're definitely going to get questions about. I think we've done Gaussian where you had to find mean and the standard deviation from conditions, like if the probability, giving a Gaussian distribution of having a value greater than like 4 was 0.2 and having a value less than -3 is 0.01. Then from that you'd normalize and you could get the values of the mean value, or I should say the mean and the standard deviation. Is everybody familiar with those? Make sure you know how to do them. I almost guarantee there's a problem like that. And another good question is how many problems on the test? And there will be 4. Now, there'll be multiple parts. You really want to know what my tests are like. Think of 4 quizzes back to back. I mean, just any 4 quizzes you take. That is what the test looks like. So the test, and I have to be a little sensitive about this, it's going to start on time. But I can't let you just go on forever because we've got another class in here. So you kind of have to know how to do the problems. And I always recommend you do the ones that you know how to do first. Then any ones you need to ponder a bit on, do those laps. And I can't overemphasize the importance of doing problems. I mean, you know, each section that's in those, and I chose the PDF for this class from that book because Stanley Chan's book is the problems are far more complicated. I mean, the problems like in the section we're messing with, they'll have problems there where you have 2-dimensional. I mean, so far, or even 3-dimensional density functions with a lot of external conditions that make it very hard to do a problem completely in like half an hour. It's just almost impossible. That's the reason I'm telling you that you need to be able to do the problems in this book. I do every one of the sections. By the way, all the solutions, the solutions manual is up there. I gave it to you. I'm not done yet, but I'm getting there. For the normalized Gaussian functions, okay, we're good on that. We talked about uniform density, right? We didn't get to analog to digital conversion. I'll deal with that later, but we did see if it's a constant density, what the mean value was and what the standard deviation was, so you can figure out the limits on a constant density. We did the exponential. This is all in chapter 2. These are the ones that you need to be familiar with. Remember, for the exponential density, it's they call it memoryless. It's the last time an event happens is like the point you start measuring time from. And that's the key. Does everybody remember the exponential density? All right, those, I think that was section 5-5. Oh, I'm sorry, 2-7. I didn't have a set of bullet points just about what the problems will be on the test, because to be frank about the problems, they are going to require like chapter 1 knowledge. I guess you need to know the binomial coefficients and stuff, like if you have the basic probability of, you draw from a deck of cards, what's the probability of drawing a heart, and then I don't know, drawing a 2, something like that. You know those problems that we did in chapter 1, that kind of a thing, or coin tosses. If you have a coin, it's a binary decision. These things are easy. If you're tossing a coin, what's the probability of getting like 1 head and 3 tails? Order doesn't matter. Well, if you call the probability of getting a head a positive outcome, then it's going to be always, it's n factorial over k factorial, n minus 1 factorial, right? P to the k, and then it's going to be 1 minus p to the n minus k. But that type of problem, be at least familiar with knowing how to do it. And I think that we did several problems in the end of chapter 1 that were related to that. Do y'all remember these things? Bernoulli trial? Okay. I'm looking at this. Check one more thing that I have here before I call it. Is the ENAC class going to have an ENAC class today, or is it online? It's in person. Oh, the switch problems, that was the other. You remember the switching problems?
Mhm.
With the probability of a network working or not working? Make sure you know how to do that. That is almost guaranteed to appear somewhere. And then quiz 1 and 2 are great starting points to make sure you know how to do. Yeah, just the quizzes themselves are, if I was you, first thing I'd do is go through the quizzes, make sure you're absolutely comfortable with the material covered in them, and you have no concerns, no areas where I don't really understand it. And then I would do the homeworks in the sections that you don't feel confident about first, and then move backwards. The last section, again, is going to be section 3-1 in the problems related, and those aren't bad at all, but it does require, if you have an f of x, y, that you can get either the f of x, the conditional probability just of x, or just of y. Assuming it's not, that y isn't a problem. And then also, remember, with the conditional probability, if I said, what is the probability of y being greater than like half and x being less than a quarter, you would have to do that integral of f of x, y over the range of values associated with the limits, with the parameters. I'm trying to think of anything else that I didn't mention. Give me one last thing to look at. You all have all your quizzes, right?
Mhm.
I'm looking at it, see quiz 4. I put those solutions up unless somehow they got taken down. Oh, quiz 4 was a Gaussian. Did you get that back? You got it back, didn't you, quiz 4?
Yeah, right here. This one.
Let me put the solution up. I have it right here. For some reason, I thought I put it up, but I do not see it. Okay, it's up now if you look. I think I've given all the quizzes back. I think you have everything. So any other questions? Because it's going to be on Monday. It'll start on time. I promise you I'll be here on time, barring an accident. And we can't go on forever, so probably it'll be over no later than 10 after 11. I'm going to have to be at least aware that there's another class coming in and stuff, okay? It'll be straightforward, 4 problems. Think of 4 quizzes back to back. That's basically what you're gonna get. If you know your material, it shouldn't be bad. You should be done very quickly.
We can say 4 problems, they'll become structured like the quiz where it's just like incrementally.
Yeah.
Okay.
You're gonna have 4 problems, multiple parts. And usually, I mean, there's nothing far afield. You're gonna get all the things we've covered and talked about. The only thing my piece of advice to everybody always is this. Do not become sleep deprived. The worst thing you can do is not get enough sleep. Then you'll make mistakes faster than you've ever dreamed of. And you want to bring coffee, tea, whatever you want in here. It's fine with me. Just don't make a mess. And there's no formula sheets. It's closed book, closed notes. If you need anything, I'll give it to you. If you want tables, if anybody wants tables, I'll provide them tables for the Q function and that the complementary function for. But I think everybody's going to use your calculators in this class for the Gaussian distributions, right? All right. So as far as I keep thinking of what else I could tell you. I always tell people get their sleep and don't be too casual about problems. You can overlook things very easily. But none of this stuff is going to be like everything that we cover. You've been responsible for is what you're going to get. So nothing is going to be given to you that's way outside the bounds. I'm not going to give you a distribution function that's crazy, like x squared over sine x from 0.1 to 0.9, something like that, where you basically are like wondering about what it even looks like. You're not going to have that, but you'll have things you're familiar with, and things like, remember, if you want the density function, you remember the one where I had I had x as sine theta. Do you remember that one? And I give you the density for the sine function. Or for the angle theta, and I want the density for the function for the function x sine of theta. That kind of a problem is legit, and that is basically that problem that we did a second ago, where you had you would have to take into account that there are 2 values. Or there one value of, I should say y, for 2 values of theta, and that type of problem. That was the one. But those kind of problems are legit. Anything else? I got nothing more profound, so we'll call it. And again, I apologize I was late. All right, I'll see you on Monday. Hey, you're going to put that recording up, right? Does everybody have access to those recordings?